In the last class, we had the solution of a vibrating rectangular membrane, the solution of the wave equation of such a vibrating rectangular membrane, and this was the solution satisfying the boundary conditions. Okay, this was the solution satisfying the boundary conditions. It is given by equation number 10. Okay, and now what is the next step? The next step is to obtain solutions that also satisfies, I repeat, the next step is to obtain the solution that also satisfies the initial conditions, which are given by equation number 3. So to obtain such a solution, we consider the double series u x y t. It's a double series in m and n. Okay, and substituting the value of umn from equation number 10, we get this particular series. This is bmn cos lambda mn t plus, this is plus bmn sine lambda mn t sine m pi by ax sine n pi by by. This is equation number 11. And what was the first initial condition? The first initial condition was that the initial displacement was f of xy, which is this. This is the initial displacement. So to obtain the initial displacement, we put t equal to 0 in the expression for u. Okay, so if I put t equal to 0, then this is cos 0, and cos 0 is 1, and here this is sine 0, and sine 0, the value of sine 0 is 0. It's 0. So only this term remains. So we have bmn from this, bmn, then we have sine m pi a by x, sine n pi b by y. So we have these two terms. And from the given initial condition, this should be equal to f of xy. Okay. Let me clear everything. Now, this is an infinite series. Okay, so suppose that f of xy can be represented by this infinite series. Then equation number 12 is called the double Fourier series of f of xy, and its coefficient can be determined in the following way. So first, what do? First, we take bmn and sine n pi by by. We take this and take the summation over n from 1 to infinity, and we call this km. Km corresponding. Let us call this km. So in equation number 2, if I take bmn, then sine n pi by by, then take the summation over all values of n, and let us call it km. Then equation number 12 becomes this equation: f of xy equal to summation over m km y sine m pi by a x. Okay. For a fixed value of y, this is the Fourier sine series. This is the Fourier sine series of the function f of xy, considered as a function of only x. So if I take a fixed value of y, then this is nothing but the Fourier sine series of the function f of xy, considered as a function of only x, because y is fixed. Then for this Fourier sine series, we can calculate the coefficients. So the coefficients of this expansion are given by km is equal to 2 by a integration over 0 to a f of xy sine m pi by ax dx. So this is the expression. Okay, so this is the expression for the Fourier coefficient. Okay, for the coefficient of this Fourier sine expansion. So kmy is given by this expression. Clear? Okay. Furthermore, this equation number 13. This equation number 13 is again a Fourier sine series. So furthermore, equation 30 is the Fourier sine series of km. And from this Fourier sine series, we can easily calculate the coefficients bmn. So the coefficients bmn is given by integration over 0 to b multiplied by 2 by b, kmy sine n pi by b y dy. So this is the coefficients of this is the value of bmn in equation number 13. Then we can substitute the value of km. In this expression, we can substitute the value of km. I repeat, in this expression, we can substitute the value of km from equation number 14. So from equation number 14, if I substitute the value of km in this equation, we get 2 times 2, that is 4, 4 divided by ab, 4 divided by ab, integration from 0 to b, integration from 0 to a, f of xy sine m pi by ax, sine m pi by ax multiplied by sine n pi by by dx dy, dx from here, dy from here. So for the Fourier coefficients of f of xy in the double Fourier series given by equation 12. So we have obtained the value of this coefficient bmn. Okay. So bmn is given by this expression. So the bmn in equation 11 are now determined in so here we have obtained bmn. So the bmn in equation 11 are now determined in terms of f of xy. Okay. Now what remains is to obtain bmn star. So we have obtained this value bmn by using the first initial condition. And what is the next step? The next step is to obtain bmn star by using the second initial condition. Okay, so to obtain this value bmn star, what do? We use the second initial condition. And what does the second initial condition give us? The second initial condition gives us the initial velocity. So to calculate the initial velocity, we differentiate u partially with respect to time t. Okay, and then we put t equal to 0 and equate it with g of xy. So this is what we have done here. So to determine the value of bmn star, we differentiate the equation 11 term-wise with respect to t. Then using the second initial condition, that is the initial velocity is g of xy, we obtain. So we take the partial derivative with respect to t, then put t equal to 0. So we get this expression. Okay, we get this expression, and equating this to gxy, we can solve b star mn. Suppose that this gxy can be developed in this double Fourier series. Then proceeding as before, we find that the coefficients bmn star bmn stars are given by this expression. So we have 4 here, a, b here, and this lambda mn, we have it here, lambda mn, and integration over 0 to b, integration over 0 to a, g xy sine m pi by ax sine n pi by b y dx dy. So the expression is almost similar with that for bmn, except that there is a lambda mn term present here in b star mn, and this term was absent in bmn. So there was no lambda mn here. Okay. And this is equal to, this is given the equation number 16. Thus, if f and g in equation number 3 are the initial conditions. So if f and g in the initial conditions are such that u can be represented by equation 11, and equation 11 is a double Fourier expansion for u, then the equation 11 with coefficients given by equation 15 and 16. So we have equation 11 is this double Fourier series with bmn and bmn star given by equation number 15 and equation number 16 is the solution of the model given by equation 1, 2, and 3. And what is the model given by equations 1, 2, and 3? There is the wave equation for a vibrating rectangular membrane. So this is the solution of a vibrating rectangular membrane. Okay. So that brings us to the end of the vibration of a rectangular membrane. Now let us look at the next problem, and the next problem is the oscillation of a circular membrane. That is the vibration of a circular membrane. Okay. Okay. In boundary value problems for partial differential equations, it is a general principle to use coordinates in which the formula for the boundary is as simple as possible. And since we want to discuss circular membranes like drum heads, we write the wave equation in polar coordinates. Because since the boundary is circular, it is best to use polar coordinates. So circular membranes occur in drums, pumps, microphones, telephones, and so on. So whenever a circular membrane is plain and its material is elastic but offers no resistance to bending. No resistance to bending means it can bend easily, freely. And this particular case, it excludes thin metallic membranes because they offer some resistance to bending. Its vibrations are modeled by the two-dimensional wave equation in polar coordinates. This is the wave equation in general is given by the second order partial derivative of u is equal to c square Laplacian of u. And Laplacian of u, when it is expressed in polar coordinates, it is given by this term inside the bracket. This term inside the bracket is the Laplacian in polar coordinates. Okay, where the coordinates are r and phi. And here c square is given by the ratio of tension to mass density. Okay. Now we shall consider a membrane of radius capital R and determine solutions URT that are radially symmetric. So we are considering a special case where the solutions are radially symmetric. Then since the solutions are radially symmetric, the solution does not depend upon phi. Okay, the solution does not depend upon phi. That means this term d2u by d phi square. Since u is independent of phi, this term should be equal to 0. Okay, since the solutions are independent of phi, this term should be equal to 0. Fine. So the second order partial derivative of u with respect to phi is 0 in equation 1 and the model of the problem. So this last term, it vanishes. So the only terms that remain are these two terms. Okay, so this equation, it reduces to a simpler form. Second order partial derivative of u with respect to time is equal to c square dou 2u by dou r square plus 1 by r dou u by dou r. This is the equation. This is the equation, wave equation for a circular membrane, and this circular membrane is vibrating, and the solutions are such that they depend only upon R. That is, the solutions are radially symmetric. And what are the boundary conditions? This membrane is fixed at the boundary. Okay, so this membrane is fixed along the boundary. That means u at r equal to capital R is equal to 0 for all times. And this is the first initial condition. This gives the initial displacement and this gives the initial velocity. So here equation 3 means that the membrane is fixed along the boundary of the circle small r equal to capital R, and the initial deflection f of r and the initial velocity g of r depends on r and not on phi, so that we can expect radially symmetric solutions u of r and t. U depends only upon r and t, it does not depend upon phi. Okay, so let us solve it. So step number 1, we have to obtain two ordinary differential equations from the given partial differential equation, and we shall get a Bessel equation. So using the method of separation of variables, we first determine solutions u equal to w times g, where w is a function of only r and g is a function of only t. So substituting u equal to wg in the wave equation and its derivatives and dividing the result by c square wg, we get this particular equation. 1 by c square g d2g by dt square equal to 1 by w d2w by dr square plus 1 by r dw by dr. Now you see that on the left hand side we have functions depending only upon time, and on the right hand side we have functions depending only upon r. So the expressions on both sides must be equal to a constant, and this constant must be negative. As we have shown earlier, we can also show here that when the constant is 0, the solution is identically 0, and also when the constant is positive, the solution is identically 0. So the only possibility is that the constant must be negative, and it is given by minus k square. Okay. Thus, this both sides should be equal to a constant. So this both sides should be equal to a constant minus k square. And this gives us two linear ordinary differential equations. First, d2g by dt square, then you multiply c square by g on both sides. So, and then you put c times k equal to lambda. So you get d2g by dt square plus lambda square g equal to 0. This is one equation. And second equation from this, we get d2w by dr square plus 1 by r dw by dr plus k square w equal to 0. So we have two equations. We have obtained two ordinary differential equations from the given partial differential equation. This equation number 6 can be reduced to Bessel's equation if we set s equal to kr. So we have introduced a new variable s, which is equal to k times r. Then 1 by r is equal to k by s, and we still retain the notation w, because w was initially a function of r, and if we substitute s equal to k times r, then we shall get a new function depending upon s, and we shall still call the new function w. For simplicity, we retain the notation w, and then we obtain by using the chain rule dw by dr is equal to dw by ds times ds by dr. And what is ds by dr? Ds by dr, as you can see from here, it is k. Similarly, the second order derivative of w with respect to r, we can obtain as d2w by ds square times k square. So by substituting these two values in equation number 6, in this equation, and omitting the common factor k square, we have d2w by ds square plus 1 by s dw by ds plus w equal to 0. This is the Bessel's equation with parameter mu equal to 0. So we have obtained one equation for g, which is given by equation number 5, and another equation for w, which is given by equation number 7. Now, since this is a Bessel equation, its solution is simple. So first, let us find solutions which satisfy the boundary conditions. So solution of equation 7 are given by the Bessel functions of the first kind j0 and Bessel functions of the second kind y0, because here the parameter nu is equal to 0. But y0 becomes infinite at the origin O, so that we cannot use it, because the deflection of the membrane must always remain finite. The deflection cannot be infinite. So y0 does not represent a physical solution. This means we have WR equal to J0 times S, and S is equal to KR, so it is J0 times KR. Okay, J0 times KR. So J0 is the Bessel function with nu with parameter 0. Bessel function of the first kind with parameter nu equal to 0. Here on the boundary. So this is the solution of W. And on the boundary, if we put small r equal to capital R, it should be 0. That is the boundary condition. So on the boundary, small r equal to capital R, we get WR, that is when small r equal to capital R, we get J0 capital R equal to 0. Okay, we get this from equation number 3. Because G cannot be 0, because G equal to 0 would imply that the displacement U is 0 identically. So G is not equal to 0. That means only W is equal to 0. Here, let me write it down in case you forget. We have U equal to W times G. And on the boundary, R is equal to capital R, we have U equal to 0. U equal to 0. So when we are on the boundary, we have U equal to 0. So U equal to 0 is possible when W is equal to 0 or G is equal to 0. But G cannot be 0. Because if G is equal to 0, then U will be 0 identically. That means the only possibility is that W at R equal to capital R is equal to 0. And there is this condition we have here. Okay. And J0 KR equal to 0. This we can easily find the points by plotting the Bessel function. This is J0S plotted as a function of S. So J0 KR equal to 0 means these are the points where the curves cut the x-axis. I repeat, these are the points where the curve cuts the x-axis. So these are alpha 1, alpha 2, alpha 3, alpha 4, and so on. So we can satisfy this condition J0 KR equal to 0 because J0 has infinitely many positive zeros given by S equal to alpha 1, alpha 2. So S equal to alpha 1, alpha 2, alpha 3, alpha 4, and so on. And the numerical values of alpha 1, alpha 2, alpha 3 are given by alpha 1 equal to this value, alpha 2 equal to this value, alpha 3 equal to 8 point this, alpha 4 equal to 11 point this, and so on. And these zeros are slightly irregularly spaced. So this equation 8 becomes, so equation 8 now implies KR is equal to lambda M. Why KR? From this KR, K times capital R is equal to lambda M, because when this KR is S, this KR is S, so when S is equal to lambda alpha 1, it is 0. When S equal to alpha 2, it is 0. S equal to alpha 3, it is 0. So that means K times capital R should be equal to alpha M, where M equal to 1, 2, 3, and so on. This implies Km is equal to alpha M divided by capital R. We call this equation number 9. So we have found the value of Km. So substituting these values of Km in equation number 8, what do we get? WMR equal to J0 KMR. This is equal to J0 alpha M by R. These are solutions of equation number 6 that are 0 on the boundary circle R equal to capital R. So these are the solutions of equation number 6. Equation number 6, let me show it to you here. Okay, this is the equation for W. So we have obtained a solution for this equation which satisfy the boundary conditions. And it is given by equation number 10. This is a solution of equation number 6 that satisfy the boundary conditions. Now let us find the eigenfunctions. Now for Wm in equation number 10, a corresponding general solution of equation number 5. And what is equation number 5? Equation number 5 is the time-dependent equation for G. So equation number 5. This is equation number 5. d2g by dt square lambda square g equal to 0. Now we know that this k, this value of k is quantized, and the values and the possible values of k are given by km. So that means lambda is also quantized, and the possible value of values of lambda are given by lambda m. Okay. So for Wm in equation 10, a corresponding general solution of equation 5 with lambda equal to lambda m c times km is gmt equal to am cos lambda mt plus bm sin lambda mt. Hence, we substitute the value of Wm and Gm. So then we get UmRT is equal to Wm multiplied by Gm, and this is Gm multiplied by Wm. We get it here. with m equal to 1, 2, 3, and so on. So this UMs are solutions of the wave equation satisfying the boundary conditions given by equation 3. That is the what is equation number 3? Equation number 3 is the boundary condition that the circular membrane is fixed along the boundary. The equation number 3 is this, and that means that the membrane is fixed along the boundary circle. So we have found solutions of this equation satisfying this boundary condition. Now what remains to be done is to find solutions which satisfy boundary condition as well as the initial conditions. So first, let us study the properties of functions satisfying the boundary conditions. So these are the functions satisfying the wave equation along with the boundary condition. And these are the eigenfunctions of our problem. The corresponding eigenvalues are given by lambda m. Okay, and the vibration of the membrane. The vibration of the membrane corresponding to UM is called the mth normal mode. It has frequency given by lambda m by twice pi hertz. Okay, and since the zeros of the Bessel function J0 are not regularly spaced on the x-axis, the sound of a drum is entirely different from that of a violin. We can call this the x-axis or the s-axis. We can also call it the x-axis or the s-axis. So since these zeros are not regularly spaced, that means the frequencies, that means the various frequencies lambda m are not multiples of lambda 1. Okay, so the sound of a drum is entirely different from that of a violin, because for the case of a vibrating string, the values of lambda m are multiples of lambda 1. Here, lambda m's are not multiples of lambda 1. Okay. The forms of the normal mode can be easily obtained from this figure. Okay, and the forms of the normal mode are shown by these circular figures. For m equal to 1, when m is equal to 1, all points of the membrane, this m equal to 1, this is the case for m equal to 1. For m equal to 1, all points of the membrane move up or down at the same time. This is the membrane as a whole vibrates. Now for m equal to 2, the situation is slightly different. The function W2R, so let me write it here. The functions W2R, and this is equal to J0 alpha 2 by capital R times small r. This function is 0 for alpha 2 r by capital R equal to alpha 1. This gives us r equal to alpha 1 r capital R by alpha 2. Okay, so the circle with this radius, is therefore the nodal line. And when at some instant the central part of the membrane moves up, the outer part moves down. So it is this case. So this radius is given by this expression, alpha 1 r by alpha 2. So the radius of this circle is given by alpha 1 capital R by alpha 2. Okay, so the whole circular disc is divided into two regions, one interior to this circle and the one exterior to this circle. So exterior to the circle, interior to the circle. Okay, and this dotted circle is the nodal line, and when at some instant this central part this interior part of the membrane, when it moves up, the outer part of the membrane moves down. This moves down, which we can see here. So the central part moves up. Here we can see that the central part moves up, the outer part moves down. Okay, and this is a 0 level. So when this moves up, this moves down. The outer part moves down. Okay, and this is for m equal to 3. Okay, so m equal to 3 has 2 nodal lines. M equal to 2 has 1 nodal line. In general, the solution UM has m minus 1 nodal lines. M minus 1 nodal lines. So when m equal to 3, we have 2 nodal lines, 1 nodal line here, another nodal line here, and when for UM we have m minus 1 nodal lines, and these nodal lines are nothing but these are circles. These nodal lines are circles. Okay. Now that we have seen the solutions which satisfy the boundary conditions, now let us look at solutions which also satisfy the initial conditions. So step 3, we have to find a solution of the entire problem. So to obtain a solution URT that also satisfies the initial conditions given by equation 4, we consider the infinite series given by URT equal to Wm times Gm summation over m from 1 to infinity. And we substitute the value for Wm. This is Wm and this is Gm. Now let us use the first initial condition, that is the initial displacement is f of r. So to find the initial displacement, we simply put t equal to 0 in this expression, and we get when t is equal to 0, this cos lambda mt, it becomes 1, sin lambda mt, it becomes 0. So what remains is only am. So we have am j0 lambda m capital R by small r, and this is equal to the initial displacement f of r. Thus, for the series 12 to satisfy the first initial condition, that is the initial displacement, the constants am must be coefficients of the Fourier Bessel series. This is a Fourier Bessel series. Must be the coefficients of a Fourier Bessel series given by equation number 13 that represents f of r. So f of r is represented by this Fourier Bessel series. Normally in the Fourier series, we have sinusoidal functions here, sine functions or cos functions here. But in this particular case, we have Bessel functions here. So we have a Fourier Bessel series. And this am, this coefficients am is given by this expression, 2 by r square j1 square lambda, alpha m integration over 0 to r fr j0 lambda, alpha m by capital R small r dr, m goes from 1 to 3 and so on. So this is the Fourier Bessel series, and the coefficients are given by this expression. Okay. Similarly, the coefficient bm can be determined from the second initial condition, that is the initial velocity. And how do we find that? We take the partial derivative of u with respect to time and then put t equal to 0, and then we can solve for bm. Okay, so the coefficients bm in equation number 12 can be determined from the second initial condition in a similar fashion. Numeric values of am and bm may be obtained from a computer algebra system, that is a special type of software like Mathematica, MATLAB, and Python, or by a numeric integration method. Numeric integration method we're going to learn in your later classes by using tables of J0 and J1. So, so the solution is given by equation number 12 with am given by equation number 14, and we can find a similar expression for bm. This brings us to the end of the vibration of a circular membrane. So let me stop recording here.